Hello there, calculus students! Welcome back to another class, and today we're moving on to Newton's method, which is one of the very best things in calculus. I love Newton's method. It can be used to solve so many interesting types of problems that, it's part of a whole family of set of solutions that are about iterative methods of solving problems, and it is so cool. I'm going to show you what happens like kind of behind the scenes as to how Newton's method works, and then I'll just show you it's kind of a simple little algorithm of steps that you'll follow to do it over again. And then in a second video, I'm going to show you how to solve it using a spreadsheet, because you're really not going to love doing this on paper. You want to do it on paper, you can, but you're not going to love doing it on paper. So if you want to do it on spreadsheets, that actually makes me a little happy. Okay, make sure you get a copy of the Newton's method handout. You're going to need that or whatever. Newton's method is, first and foremost, a method of finding the roots or zeros of an equation. In other words, the places where the function crosses the x-axis. Almost any problem can be made into a problem where you are trying to find the roots of the equation by like subtracting some number or whatever. You'll see examples of that in the homework set, but fundamentally the issue is here, you're going to have some function, f of x. Oh, some of my markers aren't as good as they used to be. And we're trying to find this value here. And Lord knows you've been doing that for a long time in math classes, right? That's what quadratic formula does, that's what completing the square does, that's what lots of methods you have learned over the years do. Now you're learning a really good way that works especially well for very complicated equations. But for right now, we're just trying to find this root right here, this value of x for which f of x is equal to 0. And your book is going to use the notation x star for that value there. It's something you don't yet know. Alright. With the Newton's method, what you're going to do is you're going to start off with a guess as to what the answer is. So let's just say, I'm going to kind of make this spread out here. Let's say we start off with x0. x0, x1, x2, x3 will be our better and better guesses eventually. Getting better and closer to x star. Clearly x0 is not x star. And one of the ways I can tell that x0 is not x star, let me just draw something here. Is that f of x0 is not 0. If x naught here was the same thing as x star, then f of it would be right here on the x-axis. F of x would be 0, but f of x naught is actually up here someplace. We have not made x naught is not the same thing as x star. Okay, but we can do something here. Now, if we wanted to, I'm going to try to do it with this edge here. If I wanted to draw the tangent line at that place, and I found where it intersected the x-axis here. See how the tangent line at that f of x naught points down to a new place on the x-axis. In fact, we can call that new place on the axis x1. x1 is not equal to x star. x1 is not the correct answer to x star, but by gosh, it isn't. x1 is closer to that answer than x naught was. Well, that's cool. All right, but I can tell that it's not the right answer, in part because f of x1 is not equal to 0, right? If x1 was equal to x star, f of x1 would be on the x-axis, but it's not. Okay, but here's the deal. Newton's method says, what if we drew another tangent line at that place? I connected it down to the x-axis. That new place we'll call x2. x2 is not equal to x1. x2 is not equal to x star, although it is closer to x star than either x1 or x0 were. But I can tell it is not equal to x star because, right here, f of x2 is not equal to 0. It's closer, but it is not equal to x0. Well, you can see what we're going to do here now. I won't use my paper this time. I'm going to draw another little tangent line in there. And that place now is x3. x3 is not x star, but it's closer to x star than x2 was, or x1, or x0. And we can just keep repeating this procedure as many times as we feel like we need to. And with each step, x of n will be closer than x of n minus 1 was. Like x of 3 is closer than x of 2, and x of 4 will be closer than x of 3, and you can do it as many times as you need to get as close as you want to x star. This is a very cool trick. Now, it's not really the kind of trick you want to do that much on paper, but it is a very slick trick, and fortunately you don't really have to draw one of these diagrams to make Newton's method work here. We're going to have a little algorithm that we can use that's going to show us how to do it here. But this is the basic pattern here, is that effectively we're going to start with a guess that we know is wrong, although hopefully we aren't terribly wrong, and then we'll get a better guess, and a better guess, and a better guess, and we can just keep repeating the process to get as good of a guess as we need. This is pretty slick. Now, the good news is this business of drawing this diagram with these tangent lines and so on is not actually necessary, because they can distill this down into an equation that will help you here. Newton's method tells us, as I showed on the middle of page 2 here, that x sub n equals x of n minus 1 minus f of x of n minus 1 all over f prime of x of n minus 1. The most important thing here is to not get confused by this n minus 1 and n stuff. I don't mean like I took x of n and I subtracted 1. I mean x of 1 lower than that. So like when I'm finding x3, my third guess, it'll be equal to our second guess minus f of our second guess all over f prime of our second guess. That's the main thing. That's why I highlighted that there in yellow. That's an important thing to keep straight about what we're doing with Newton's method. This is such a cool trick. But I don't love doing it on paper or on a whiteboard or whatever, but I'm going to try to do one here for you. This is on page 2. It's example 446 from your book. It says, using Newton's method, here I'll even label that, it's 446. I wonder if another one of these markers is better. Let's try this one. Oh yeah, that one's super dark. Okay. Problem 446. The equation that we're working with is f of x is equal to x cubed minus 3x plus 1. Okay. This function, I don't know off the top of my head what it looks like here, but there apparently is going to be some kind of root of the equation, some kind of zero of the equation in the interval 1 to 2. Alright, and we could pull it up in Desmos or whatever and take a look at it or whatever, and Desmos even lets us click on the roots and so on, but this is actually behind the scenes how Desmos is doing it. Alright, so what we're going to do is we're going to find the roots of this equation, the first root of this equation, and it tells us to let the first guess be equal to 2. Alright, so we're just going to make ourselves a little method here. Oh wait, but in order to do this, we need this f prime. So we're going to need to know the derivative of this function. We need that handy here. It's just 3x squared minus 3. We'll need that, okay. So let's see here. I'm going to make myself a little table here. If n was equal to 1, like now we're looking for x1, in order to do that, we're going to need x of n minus 1, which in this case is x of 0. Well, that's given to us in the problem. It's a 2. We're going to need, according to Newton's method up here, we're going to need f of n minus 1. F of x sub n minus 1, like that. Alright? In this particular case here, so that would be f of x0. See, n is equal to 1. So n minus 1 is 0, x0, f of x0, x0 is 1, I'm sorry, is 2. You plug that 2 into this equation here, and you get 9. No, I'm sorry, you get 3. You get 3, sorry. I'm working through what happens down there on the bottom of page 2 of your handout. And we're going to need f prime of x sub n minus 1. Alright, that means you're going to plug this number, we're looking for x0. Well, x0 was equal to 2. Plug that in here, you're going to get a 9. And that gives us then our way to figure out x of n. Let's see, that's right here. X of n minus 1 divided by f of x n minus 1 divided by f prime of x n minus 1. You crank those through here and you get 5/3. Alright, so when n is equal to 1, x of n, our first guess, we had a 0th guess of 2, is now 5/3. Let's make our second guess. To make n equals 2, alright, that means this column will be x of 2 minus 1, or x of 1. Well, actually, that's the one we had right here. It's 5/3. And then, alright, well, we'll work through on the bottom of page 2 here. That means f of x1, and it's equal to 0.63-ish. And we need f prime of x1, which turns out to be 5.33-ish. And that means that x2 is equal to 1.5486. Alright, moving on. Now we're looking for x3. x2 is actually just equal to this one. Right? That's what this was, x2. Now x2 is over here for x3 minus 1. Alright. That means that f of x2 is 0.068-ish. And f prime of x2 is equal to 4.19-ish. Therefore, x3, right, xn, where n was 3, becomes 1.5324. Let's find x when n is equal to 4, our fourth guess. All right, well, the third guess was this. All right, f of the third guess was this. F prime of the third guess was this, and it keeps going. And x4 turned out to be 1.53208889. And we could keep going as many times as we wanted. Notice that the solution went from 2 to 1.66 to 1.54 to 1.53 to 1.532. Notice we're getting closer and closer to an answer here. Somewhere near 1.530828888989, or whatever that number is going to be our solution. Cool. And how can I tell that we are getting awfully close to the solution? Because f of that, remember, would be equal to 0 if we were at the solution. Well, that's getting pretty darn close to 0. And in fact, if we iterated this one more time, on the fifth line, as you can see on the little thing at the bottom of page 2 of the handout, I mean, we get something times 10 to the negative 7th. We're getting some pretty tiny little number, not times the 7th, times 10 to the negative 7th. We're basically getting a 0. We could iterate again, though, as we get as close as we want to the final solution, but it only approaches it. It never quite gets there. Now, we're going to do more examples of Newton's method, and the textbook is great. Notice, though, that I kind of made it look like a table here. And that's because Newton's method is really something you want to do in a computer program or on a spreadsheet, okay? I mean, you can see how this quickly became error-prone and so on, writing these out on paper. In the second part of this video, I'm going to be showing you, well, the second video or whatever, I'm going to be showing you how to do this on a spreadsheet, because I think you're going to be a lot happier with that. I just want to take the time while they're still doing this, though, here at the Whitey board, to help you steer clear of a trap. This is happening on page 3 of your handout. Alright. Remember, what Newton's method is really for is for finding the roots or zeros of an equation. Well, one type of equation that you like to find the roots of is the first derivative of an equation, because that can help you find critical points or maxima and minima and stuff like that. So it can often be the case, like for example, I'm going to look at problem 442 in the book. This is on the middle of page 3 of your handout. So let me just say here, this is problem... Yeah, let me fix that. I misspelled it. This is going to be problem 442 at the back of the chapter there. The back of the section of the book. And it's saying find the max of this function. F of x is equal to x cubed plus 10x squared plus 15x minus 2. All right. Actually, at the bottom of page 3 even showed you what a graph of that thing looks like. And it swings through something like this. And so there's some max right here. And they want us to find the value of x, where that is that maximum. Okay, well, hey, there's an f of x in Newton's method. We must be on the right track, right? I'm afraid not. Here's the deal. We don't want to find if we tried to apply Newton's method to this function, we'd be finding its roots, or zeros. We'd be finding places like this. How do you know which root you're going to find? Generally speaking, you pick a starting guess that's closest. Like if you find a starting guess that's closest to this root, you'll get this one. If you choose one that's closest to this root, you'll get this one. All right? But that's not what we're trying to do here. We're trying to find the maximum, the place where the derivative was equal to 0. In other words, this is not the function that we are trying to use Newton's method on. And I would make a suggestion here. When it's a problem like that, this is not the function we are trying to take find the zeros of. Don't let them call it f. You have power here. Call it g or something instead. Okay? Because that is not the function that you are using in Newton's method. The function you are using in Newton's method is going to be the derivative of g, which we're going to call f of x. And it's going to be equal to 3x squared plus 20x plus 15. Let this be your f of x. Because this is the one we want to find the zeros of. This is the one who we need to find the zeros of so we can find the places where the slope is equal to 0 here. See what I did here? I used my power to say, don't let them trick you and call this function, original function f, if this is not the function that you're trying to use Newton's method on. Call it something else. You have the power to rename these variables here. All right, in this case here, I actually just made a little table on page 4 that looks exactly like what I did on the board before, where I said, here's n, so then we're going to need to know x of n minus 1. Like, for example, when we're trying to find guess n equals 1, we'll need to know the initial guess, because that'll be x of n minus 1, or x of 0. That's our initial guess. And then when I made this chart here, I think I used an initial guess of x is equal to -6. All right. And then I said I'll need to know f of x sub n minus 1, and I'll need to know f prime of x n minus 1, and I'll need to know x of n. And I have values here. The first row is no big deal. And then we did a second guess, and a third guess, and a fourth guess. And by that time, the entry right here, f of our guess, was already times 10 to the negative 10th power. I mean, these are very, very small numbers. They're basically equal to 0. And notice that in the last column, x of each of these guesses here, x0 was -6, but by x1 we were at -5.8, and in fact, x3 and x4 were both the same number already. We're basically, to within the accuracy of the spreadsheet that I used to make this table, already at the solution here. Which means that at x equals -5.8054, this function has a 0. Which means this function has a max. So this place here, where we were looking for, is at x equals -5.8 whatever. Okay? This is pretty slick. There are so many interesting types of problems in science and engineering and business and computer science that use these kinds of iterative methods. You can see why it's called an iterative method, because you just keep repeating the procedure. Newton's method is an iterative method that is so cool and can be used to solve all kinds of interesting problems, but it can get you to the wrong answer. And like, I actually, at the bottom of page, what would that be, page 4, I actually showed you an example from the book where the method actually was looking for a particular root. See, it says root sought, but it actually found a different root instead. Basically, that's going to happen if your initial guess is bad. If you were too far away from the correct answer when you picked your initial guess. And your book wastes a lot of ink, not wastes, invests a lot of ink on that issue. And that's actually one well, that's actually hugely important in science and engineering and so on. But here's and modeling and so on. But there's a whole course you can take in computer science called Numerical Methods at Purdue. It's Computer Science 414 that explains how to make a good guess and how to know if your guess is close enough that it'll find you the right root of the equation. And that's all really cool, but there's literally a whole course on how to do that. I don't know that I think a couple paragraphs in our calculus book is a good investment of time to start narrowing that kind of problem down. But being aware that, like, if I had chosen a really, like when we were looking for this maximum here, if I had made a really crappy guess, like I thought it might be over here, we might have ended up with the wrong solution. Like it might have found us this minimum rather than this maximum. Okay. Most of the time, if you first make the graph in Desmos and then take a look and say, okay, the answer is clearly somewhere near -6, then you're going to be fine. Okay. So that's really the main thing I wanted you to point out about that. Your book spends a fair amount of ink on that there. But here's the deal. Honestly, I love Newton's method, and I'm going to show you a couple things about Newton's method in the next video here. And doing it on paper is really error-prone. If you have any spreadsheet skills at all, you're going to be way happier doing this on a spreadsheet. I can't even count the number of times in my life I've had to, when I was doing research and stuff like that, I had to write Newton's method into a computer program to solve a problem for me. This is really fundamental, these kind of techniques for finding solutions to roots of equations that are complicated. But I'm going to show you some of that stuff in the next video, alright? So go ahead and you're going to watch the next part of the video by following the next link, and I'll be showing you something on the computer screen.